Alright, thanks for watching. And today we'll do some really cool PDEs because I'll talk about reflection of waves. And this is sort of a PDE where we'll just work out theoretically what's gonna happen and then we'll see that physically it actually makes sense. So suppose now you have the wave equation UTT equals to c squared uxx, but unlike previously where we have the wave equation on the whole line, this time we'll just have the wave equation on the half line. And the interpretation is, suppose you have your waves as usual, but this time you have some wall or some barrier at x equals 0. And then you want to figure out what happens to your wave. And not only that, let's say the wave at 0 is 0. So let's say u of 0t equals 0. And our usual initial position and velocity. So u of x0, it's phi of x. And ut of x0 is psi of x. So again, you have the wave with, let's say, initial position phi and initial velocity psi, and you want to figure out what happens. And before we do that, let's predict the behavior. That's another reason why I like PDEs. You can actually guess what's going to happen to your solutions most of the time. Now, what's going to happen? Well, as we know from the wave equation, this wave, initial wave, splits up into smaller waves, maybe something like that. And notice, this one on the right just travels freely. That's okay. But the one on the left, it's kind of interesting because for at least a short amount of time, nothing happens, right? It's just like the usual wave equation. So we'll see for a short time, the solution is given by the usual solution. But once it hits the wall, bang, and it doesn't travel to the left anymore, it will travel to the opposite direction. And this is what we want to show basically with our formulas. And the cool thing is the method is exactly the same method as for the heat equation. Because what did we do? For the heat equation, we only had phi on the half line, which we also do here now. And we just oddified phi because we needed the value at 0 to be 0. And indeed, we're going to do the same thing here, except we do it for phi and psi. So step 1, just oddify phi and psi. I'll try not to laugh, but it's pretty funny. First of all, let's have FOD. FOD of x, phi again, phi of x, for x positive, 0 for x equals 0, and minus phi of minus x for x negative. So again, that's a typical picture. This is phi, and then FOD, it's here, right? It's the same as phi for x positive. It's 0 at 0, and it's minus phi of minus x for negative. So FOD is like the odd reflection. And before we only had FOD, but now we have its brother, PSOD. And so PSOD, it's same thing, psi of x for x positive, 0 for x equals 0, and minus psi of minus x for x negative. Okay. Very good. So we have FOD and PSOD. And what we want to do now, we want to solve the wave equation on the whole line, but with FOD and PSOD. So, it's like in Super Mario where suddenly you have two bosses at the same time. And like, yeah, they're like two evil brothers, FOD and PSOD. And you have to conquer them. Okay. So, now solve UTT equals c squared uxx, again on the whole real line, with initial condition FOD and initial velocity PSOD. should have seen me in lecture. I was like dying. So now I'm like controlling myself. But the cool thing is this becomes a wave equation on the whole real line. So we can solve this using d'Alembert. So d'Alembert just says u of xt, it's 1/2, usually phi of x minus ct, but phi of x minus ct here, plus phi of x plus ct, plus, I believe, 1/2c integral of x minus ct to x plus ct of psi of s ds. And essentially, all we need to do is to deconstruct this formula. And by the way, so why does this solve our original problem? Well, same as before. So first of all, it solves the PDE on the half line because it solves it on the whole real line. So we have a harder problem, right? So we solved the harder problem, therefore we solved the easier problem. And also, why do we have the other condition that it's 0 for x equals 0? Because u of 0t, it's 1/2 phi of minus ct plus phi of ct plus 1/2c integral from minus ct to ct of psi s ds. Now, psi is an odd function, and the integral of an odd function over a symmetric interval is 0. So this, by construction, it's 0. This one, well, phi of minus ct, it's minus phi of ct. So this also cancels out, you see? And therefore we get that it's 0. Again, just by construction, so by using even oddification. And you can also check the other things. If you plug in t equals 0, you basically get phi of x here, which gives you a phi of x if x is positive. And same thing here. You get, I guess, best case you get 0, but then for derivative-wise, you will always get c. So this works. Trust me, and really, as I said, the only thing we still need to do is to decompose this formula. So, let me do it here. Now, here's the thing, okay? This definition, right, changes whenever this is positive or this is negative. So we do have to split into two cases. One where this becomes negative, and the other one where this is positive. So case 1, suppose x minus ct is positive. And notice, what's the interpretation? This means ct is less than x, so t is less than x over c. So I interpret this as saying t is small. T is small, and kind of it's the case before you hit the wall. Then, u of xt, it's again 1/2 phi, again of x minus ct, plus phi of x plus ct, plus, again, 1/2c integral of x minus ct to x plus ct psi of s ds. Now, don't need this anymore. Look, we know x minus ct is positive. So this is positive. And in particular, remember, if the argument is positive, phi just becomes phi. So this becomes 1/2, so 1/2 phi of x minus ct. And now remember, x is positive, time is positive, so this is also positive. So it's phi of x plus ct plus 1/2c integral of a positive thing to a positive thing. And you see, on this positive interval, psi is just psi. So this is the explicit formula for the first case. If t is small, and you may notice, I hope you do, that this is just the usual d'Alembert's formula. So basically, what is this saying? Just like we predicted, if we have this wall, because after all, you might wonder why. Okay. If we have this wall, then if we start with a wave, this one splits up to the right, this one splits up to the left, well, for small time, nothing different should happen. And in fact, this is what we're saying. Nothing is happening. I don't know why I wrote p of x minus ct. Nothing is happening. And therefore, we're given by the usual d'Alembert formula. Now, the interesting thing is if time becomes large. So case 2. And okay, so case 2. X minus ct is negative. Okay, I'm not going to do the case equals 0. You can work it out. It's not very interesting. Then that means, again, t is greater than x over c. So time is large. Then we get something new. Then u of xt, that's 1/2 of, again, thought of x minus ct plus thought of x plus ct plus integral from x minus ct to x plus ct psot of STS. Okay, now x plus ct is still positive. That's not a problem. The new thing is x minus ct becomes negative. And we get something new. So that becomes 1/2, again by definition, minus phi of minus x minus ct plus, again, phi of x plus ct. And again, we have something new here. This becomes negative, right? So it's best to just split it up. Integral of x minus ct to 0 of psot of STS plus integral from 0 to x plus ct of psot of STS. Now, on this negative interval, psot is just minus psi of minus s. Yes? On this positive interval, psot is just psi. Now, all we need to do is to clean up the formula. So 1/2 of, I guess, minus phi of, it becomes, if you want, ct minus x plus phi of ct plus x, if you want. And then here, oh, I forgot the 1 over 2c. Now, here we just use a u sub, so it's 1 over 2c, and if you want, again, pb minus s, then what we get is, okay, sorry, so if you do minus s here, this becomes ct minus x, and then this is 0, and then minus ds becomes minus dp, so psi of p, dp. And then plus 1 over 2c, integral from 0 to x plus ct, psi of STS. And the nice thing is, we do have the two integrals that come together into just one integral. So let me just check if that's correct. Yep. So what we get then, in this case, u of xt, it's 1/2, again, let's do this, phi of ct plus x minus phi of ct minus x plus 1 over 2c integral of ct minus x to ct plus x psi of SDS. So, again, here is, if you want, we started with u being, the formula for FOD and SOD. We just rewrote everything based on the cases. And it turns out even here, we do have a nice representation in terms of sums and integrals. And I like you to compare now the two things that are different. First of all, it's not x plus ct and x minus ct anymore. It's ct minus x and ct plus x. We have this extra minus sign. And now, instead of integrating from x minus ct to x plus ct, we're integrating from ct minus x to ct plus x, which is good because now all those terms are positive. Now, as I said, what does that mean physically? We have the wall here, and we had the wave. Okay, so that's x equals 0. We have the wave that splits up again into two parts. One part that doesn't change, and that's the ct plus x part. It just goes to the right like that, and again, this part doesn't change. This one, well, look. This wave here, this is, if you want, the x minus ct part. It was supposed to go to the right. It was supposed to be x minus ct. But this is not what's happening. What's happening is this wave here is just collides on the wall and then just goes on the other direction. So it goes like this, not x minus ct, but minus that, ct minus x. And that's precisely what we have here, ct minus x. In fact, it seems it gets reflected downwards as well. Which, by the way, it's kind of similar to the 3 blue, 1 brown problem with the colliding blocks. But here we have almost colliding waves. And therefore, this ct minus x term appears here, but also here as well. So, it's kind of neat. And last thing I want to say, you can also explain this with something called the domain of dependence, which intuitively speaking is, given a value of x comma t, which values does u of xt depend on? And what we have here in case 1, we have our usual domain of dependence for the wave equation. So if, let's say, t isn't very big, so here let's say xt, then we have the domain of dependence, which is just given by this triangle. And again, this is a whole different story. X minus ct 0 and x plus ct 0. Because notice in D'Alembert's formula, if phi and psi are 0 here, then it forces u to be 0. So in other words, u just depends on the values of u on that triangle. Now, and then, as I said, in case 1, we just have this usual case. But in case 2, we actually have a different domain of dependence. Because suppose you have a case like here. This is now x comma t. Then, what we're supposed to have is a domain of dependence like this. Just a triangle. But here, we don't quite have this. So this is still x plus ct. 0. But then ct minus x becomes this actually. Ct minus x comma 0. So in this case, we don't have a triangle of dependence anymore, but kind of a reflected triangle. You see, it's supposed to be like that, but the triangle gets reflected, and we get this new quadrilateral of dependence. And kind of the cool thing is, and I'm not going to do this, it's very complicated, but if, let's say you have two walls, one at 0 and one at 1, then you have actually infinitely, maybe not infinitely, but you have a bunch of reflections, and in this case the quadrilateral reflection becomes some kind of weird shape like this. because we have so many reflections on the two walls. So just give you a taste. Wave equation is a pretty cool thing. I still prefer Laplace's equation because it's even cooler, but I think that's very neat. Especially, this is one of the reasons I like PDEs. You're like being your own little creator here, right? You have your equation and you're predicting what's gonna happen. In fact, mathematically, you're showing that this is true. It's you're seeing what you've created is correct. All right, I hope you like this, and if you want to see more math, please make sure to subscribe to my channel. Thank you very much.